November 1944. A Japanese Zero fighter, its engine screaming, drops into a near-vertical dive toward the deck of the USS Essex. The pilot has one mission, one purpose, one destination, and nothing will stop him from reaching it. American gunners track the aircraft, their 5-inch guns firing frantically, filling the sky with black puffs of exploding shells. The pilot grins. He knows the statistics. Anti-aircraft fire has to score a direct hit or explode within a precise distance to bring down an aircraft. The odds are in his favor. He is 200 meters from impact when something impossible happens. A shell explodes exactly 20 meters from his aircraft, at precisely the optimal distance to shred his plane with shrapnel. He has no time to wonder how. The Zero disintegrates mid-air, raining burning debris into the ocean. The pilot never knew what killed him. Neither did Japanese intelligence, despite desperate attempts to discover the secret. The Americans had created something that should not have existed with the technology of the era. They had built a fuse that could think. The problem facing Allied forces in 1940 through 1942 was existential. German bombers were devastating British cities. Japanese aircraft were sinking warships across the Pacific. Anti-aircraft artillery was fundamentally limited by its fuse technology. Traditional shells used time delay fuses, where gunners had to estimate the target's altitude, calculate the shell's flight time, and set a mechanical timer before firing. If the estimate was off by even a second, the shell exploded harmlessly in empty sky. Contact fuses, which detonated on impact, were even worse for anti-aircraft work. An aircraft is a small, fast-moving target. The probability of a direct hit was microscopic. Gunners were essentially firing into the sky and hoping. The mathematics were brutal. In 1942, it took an average of 2,500 anti-aircraft shells to bring down a single enemy aircraft. 2,500 shells for one kill. The cost in ammunition, gun barrel wear, and crew fatigue was unsustainable, and aircraft kept coming. What the military needed was a fuse that could detect when it was near an aircraft and detonate automatically at the optimal distance. The concept was simple. The engineering was anything but. To work, the fuse would need to transmit a radio signal, receive the reflection from the target, calculate the distance in milliseconds, and trigger detonation at precisely the right moment. It would need to do all of this while surviving the launch forces of an artillery shell, which could exceed 20,000 times the force of gravity. It would need to function reliably in any weather, at any altitude, at any time of day or night. It would need to be small enough to fit in the nose of a shell, light enough not to affect ballistics, and cheap enough to manufacture by the millions. The device would need to contain a radio transmitter, a receiver, vacuum tubes, a battery, amplification circuits, and a detonation mechanism, all in a package the size of a soda can. In 1940, this was considered impossible by most engineers who examined the problem. Radio technology of the era used vacuum tubes that were fragile, bulky, and power-hungry. Miniature batteries barely existed. The tolerances required seemed beyond mass production capability. But impossible was not an acceptable answer when cities were burning and ships were sinking. The task fell to the National Defense Research Committee, specifically Section T, based at the Applied Physics Laboratory at Johns Hopkins University. The lead scientist was Merle Tuve, a physicist who understood that conventional approaches would fail. He assembled a team of the best radio engineers, physicists, and mechanical designers available. They were given unlimited funding, top priority for materials, and one directive: make it work. The team started by accepting that they would need to invent new technologies just to make the fuse possible. Standard vacuum tubes would never survive the launch shock. They developed new miniature tubes with reinforced elements and shock-absorbing mounts. Standard batteries would die instantly under launch acceleration. They created new battery designs using reserve electrolyte systems that activated only after firing. The radio circuit itself was revolutionary. Operating at around 200 megahertz, it transmitted a continuous signal and measured the Doppler shift in the reflected signal to determine range. As the shell approached the aircraft, the frequency of the reflected signal would increase. When the shift reached a predetermined threshold indicating optimal detonation range, the circuit would trigger. The physical forces involved in artillery firing are difficult to comprehend. When a 5-inch shell leaves the gun barrel, it accelerates from 0 to over 800 meters per second in less than 20 milliseconds. The components inside the fuse experience forces exceeding 20,000 Gs. For comparison, trained fighter pilots can barely withstand 9 Gs before losing consciousness. The fuse components had to survive forces more than 2,000 times greater, and they had to survive them while remaining functional. Every component was a miniature engineering masterpiece. The vacuum tubes were designed with hairpin filaments only millimeters long, mounted on springs that could flex during launch but maintain electrical contact. The tubes themselves were filled with a special gas mixture and sealed in glass envelopes tested to withstand the shock. Each tube was individually tested by dropping it from height onto a steel plate. Only those that survived made it into production fuses. The battery system was equally ingenious. A reserve battery design kept the electrolytes separate from the plates until needed. During launch, the G-forces would break an internal ampule, mixing the components and activating the battery. This meant the battery had unlimited shelf life before firing and would provide power immediately after launch. The entire power supply generated only about 1.5 volts, requiring the circuit design to operate on minimal power while still achieving the sensitivity needed to detect aircraft at useful ranges. The radio transmitter and receiver shared the same antenna, a small metal stub protruding from the nose of the fuse. The antenna had to survive supersonic airflow, rain, and potential icing while maintaining the proper impedance for the circuit. The shape was carefully designed through hundreds of wind tunnel tests to minimize aerodynamic interference while maximizing radio performance. The signal processing circuit was the heart of the system. It had to distinguish between valid aircraft reflections and false signals from ground, sea, clouds, or other shells. This required careful frequency selection and filtering. The chosen frequency of approximately 200 megahertz was a compromise. Higher frequencies would give better resolution but required smaller components. Lower frequencies would be less affected by weather but would give poorer range discrimination. The circuit used a super heterodyne design with multiple stages of amplification and filtering, all accomplished with just 5 vacuum tubes. The final stage drove a thyrotron tube, a gas-filled switch that could handle the high current needed to trigger the detonator. The detonator itself was another carefully engineered component. It had to be safe during handling, storage, and loading. It had to arm itself automatically after firing, but only after the shell had traveled far enough from the ship to avoid premature detonation near the gun. This was accomplished with a centrifugal arming mechanism. The shell's rotation during flight would cause spring-loaded pins to move outward, aligning the detonator train with the main explosive charge. The system was fail-safe. If the radio circuit failed, the fuse would not detonate at all. Better to waste one shell than risk killing your own gunners. Every fuse contained approximately 200 individual components, many of them custom designed and manufactured to tolerances measured in thousandths of an inch. The entire assembly had to be done by hand under clean room conditions to prevent contamination that could cause circuit failures. At peak production, American factories were producing over 70,000 proximity fuses per day, each one a miniature technological marvel, each one tested to ensure it would function when needed. The security surrounding the proximity fuse was extraordinary. The device was classified at the highest level. Even the existence of the program was secret. Shells containing proximity fuses were painted with special markings and handled separately from conventional ammunition. Gunners were told simply that these were new, improved fuses and were not given details of how they worked. The greatest security concern was that a dud shell might fall on enemy territory intact, allowing reverse engineering. For this reason, the proximity fuse was initially restricted to use over water only. If a shell failed to detonate, it would sink to the ocean floor, keeping its secrets safe. This restriction would not be lifted for use over land until the urgency of combat demanded it. The first combat use of the proximity fuse occurred in January 1943, when the USS Helena engaged Japanese aircraft during the Guadalcanal campaign. The results were immediate and dramatic. Gunners reported that shells seemed to know where the aircraft were, exploding at precisely the right distance even when the aircraft were maneuvering. Japanese pilots, used to dodging the predictable bursts of time-fused shells, found themselves flying into walls of shrapnel that appeared without warning. The kill rate climbed immediately. Before the proximity fuse, the average was 2,500 shells per aircraft destroyed. With the proximity fuse, the number dropped to under 100 shells per kill. Some engagements achieved ratios of 40-1. The improvement was not incremental. It was revolutionary. The psychological impact on enemy pilots was substantial. They could no longer rely on evasive maneuvers to avoid anti-aircraft fire. The shells followed them, exploding at the worst possible moment. Kamikaze attacks, which relied on pilots surviving long enough to reach their targets, became far more dangerous. Pilots who had accepted death on impact now faced death long before reaching their target. The Battle of the Philippine Sea in June 1944 demonstrated the fuse's effectiveness on a massive scale. Japanese aircraft launched over 400 planes against the American fleet in what would become known as the Great Marianas Turkey Shoot. American ships equipped with proximity-fused ammunition created an almost impenetrable defensive barrier. Over 300 Japanese aircraft were destroyed, many of them by proximity-fused shells. The Japanese lost the majority of their carrier air power in a single day. The secrecy surrounding the fuse meant that Japanese intelligence struggled to understand why their aircraft losses had suddenly skyrocketed. Captured pilots reported shells that seemed to home in on aircraft. Japanese engineers examined shell fragments and found unusual electronic components, but could not reverse engineer the complete system. They never developed a comparable technology during the war. The Germans faced similar mysteries when Allied bombers over Europe began using proximity-fused shells in defensive turrets, though these applications were limited due to the risk of dud shells falling on occupied territory. The restriction on using proximity fuses over land was finally lifted in December 1944 during the Battle of the Bulge. German forces had launched a massive surprise offensive through the Ardennes forest. American artillery, including proximity-fused shells, was brought to bear against German infantry and armor. The results were devastating. Traditional artillery shells exploded on impact with the ground, with much of their shrapnel directed harmlessly into the earth. Proximity-fused shells detonated in the air above German positions, showering troops with shrapnel from above where they had no cover. The effect on exposed infantry was catastrophic. Entire German units were decimated by airbursts that seemed impossibly precise. German commanders reported that American artillery had become far more lethal than anything previously experienced. They had no explanation for the change. The Battle of the Bulge marked a turning point. The proximity fuse had proven itself not just in anti-aircraft roles but in traditional artillery applications. The technology that had been developed to shoot down aircraft was now filling battlefields with precisely timed airbursts that no entrenchment could protect against. By the end of the war, over 22 million proximity fuses had been manufactured. They equipped shells for 5-inch naval guns, 3-inch anti-aircraft guns, and even some rockets. British forces received proximity fuses for defense against V-1 flying bombs, achieving remarkable success rates against the German cruise missiles. The fuse had gone from impossible concept to mass-produced reality in less than 4 years, a testament to American industrial capacity and engineering innovation under pressure. The proximity fuse has been called one of the 3 most important technological developments of World War II, alongside radar and the atomic bomb. Unlike the atomic bomb, which was used twice, or radar, which required large installations, the proximity fuse was used millions of times in diverse combat situations and proved its value in every application. The technology represented multiple breakthroughs simultaneously: miniaturization of electronics, ruggedization of vacuum tubes, development of reserve batteries, and creation of reliable radio frequency circuits that could be mass-produced. Each of these advances had implications far beyond the immediate military application. The Germans attempted to develop similar technology but never achieved a working system. Their VT fuse program, begun in 1943 after examining captured shell fragments, failed to produce a reliable combat-ready device before the war ended. The Japanese made no significant attempt, lacking the industrial capacity and radio technology expertise required. The British had actually begun proximity fuse development before the Americans and shared their research freely. But it was American industrial capacity that transformed the concept into millions of functional devices. The Anglo-American collaboration on the proximity fuse was one of the most successful technology-sharing programs of the war. The post-war impact of the proximity fuse technology was immense. The techniques developed for miniaturizing and ruggedizing electronics became the foundation for guided missile systems. Modern air defense missiles use direct descendants of the proximity fuse technology, though now with solid-state electronics instead of vacuum tubes. The Doppler radar principle used in the fuse influenced everything from police radar guns to collision avoidance systems in automobiles. The manufacturing techniques developed to produce millions of complex electronic devices under wartime pressure helped establish the foundation for the post-war electronics industry. Modern military forces take proximity-fused ammunition for granted. Every anti-aircraft system, every artillery shell designed for airburst, every smart munition that detonates at optimal range owes its heritage to the wartime crash program that produced the VT fuse. The fundamental principle remains unchanged. Detect the target, calculate the optimal detonation point, and trigger at precisely the right moment. What required 5 vacuum tubes and analog circuits in 1943 now fits on a chip smaller than a fingernail. But the core concept that seemed impossible to engineers in 1940 has become the standard for precision weaponry. If you are finding value in understanding how tiny innovations changed the course of history, sharing this story helps more than you know. The proximity fuse killed more enemy aircraft and personnel than any other single weapon technology of the war. It protected Allied ships from kamikaze attacks. It devastated German positions during the Battle of the Bulge. It demonstrated that complex electronics could be mass-produced reliably under extreme pressure. But perhaps most importantly, it proved that seemingly impossible engineering challenges could be solved when necessity demanded it. In the vast catalog of World War II innovations, the proximity fuse stands out not just for its effectiveness, but for the sheer audacity of its engineering. A radio transmitter that could survive 20,000 Gs, a battery that activated itself during firing, a circuit that could distinguish aircraft from clouds while traveling at supersonic speed, a detonator that armed itself through centrifugal force. All of this in a package the size of a soda can, manufactured by the millions, reliable enough to trust with the lives of thousands of sailors and soldiers. The tiny fuse that filled the sky with burning metal was more than a weapon. It was proof that engineering brilliance, properly focused and supported, could accomplish the impossible. It changed warfare permanently, and its descendants continue to protect forces today, 3/4 of a century after that first successful engagement over the Pacific.